And now, and this is a nice feature, you realize when you go to the time-dependent version, you actually do not need the final state here. So there is no final state dependence in all this expression, but here with the state itself. So you can actually apply the closure relation. The sum over all states is unity. Essentially you can take them out and you end up with this expression here. And this shows you that the total photoabsorption cross-section is an initial state property only. Do you have an idea why this is so important? This brings density function theory into play in the response theory, because one knows in density function theory anything which is a property of the ground state can be expressed exactly in density function theory. So even here, in excitation to God knows which energy, sum over all possible channels turns out to be a ground state property. If the initial state is a ground state, it can be described by density function theory very accurately. And this is really what GFT has capitalized on quite a bit in all the applications. And you could also formulate that in a different way, which is then very elegant and opens another venue how to interpret photoabsorption. In a way, this expression is the Fourier transform of the time-dependent dipole correlation function. Because here you see, this is one dipole operator, which does not carry any time dependence if you wish. And this is just a unitarily transformed dipole operator with the polarization, always pi is the polarization. And this is just the Heisenberg form of the operator, right? So we can express that, it's just the same expression, just rewriting it here as basically the dipole operator at 0 time times the dipole operator conjugate at time t, propagated in the Heisenberg picture with your Hamiltonian. Take the expectation value of that, and this is nothing but the dipole correlation function, time-dependent dipole correlation function. You take the Fourier transform of that, and you end up with the absorption cross-section. Of course, the question is, maybe for you, how we actually come to this time-dependent formulation. You might know the Fermi's golden rule, just in the energy domain with the delta function, and that's another little exercise I want to do for you here, how to do that. It's not only me who's coughing. So, Fermi's golden rule, as we all know it, for photoabsorption. And of course, you also take our favorite atomic physics book from Harald Friedrich to look up this formula. Decided. So this is from Friedrich, atomic physics. I think there's a new edition. One is from 1998. So probably the page has changed. There it's page 111. And it tells you that the photoabsorption cross-section is essentially the sum, again over the final states, clearly, 4 pi squared alpha f, that's the fine structure constant. That's kind of the coupling constant for electromagnetic interaction, which it is, of course, with the photons. And then h bar over omega. And then we have the familiar matrix element, dipole matrix element, E initial squared. Yeah? And now comes this stupid term which is really annoying in the first semesters, I think, which contains a delta function. One never knows what to do with it. Delta E final minus E initial, which is energy conservation. It simply tells you that you are taken with the photon from your initial energy of the initial state to the final state. And if this doesn't match, there is nothing to be absorbed. That's quantum mechanics. Okay, so I should also tell you why I write dV here all the time very carefully. This is, of course, because I hopefully got the right prefactor. which means I am actually in the velocity gauge for the dipole operator, and this is then momentum over mass of your electron. Yeah? You probably know the different gauges. You can have length gauge and you can have acceleration gauge. Come to that shortly. But this is what comes out if you take your normal kind of minimal coupling. I think it's E over C times A vector potential squared if you make this replacement, yeah, in your kinetic energy. Then basically this dipole operator is resulting. And the rest of the vector potential, the strength of kind of your source, is absorbed in the prefactor, because this is already cross-section, and of course we are in a linear regime, therefore it's not so important, yeah, how big that is. It doesn't depend on the strength of your electromagnet, since you only absorb one photon anyways. Okay, so this is the dipole operator and velocity gauge, and as I said, that's just a projection for the polarization you have. Now, to really get to this form up here, to the time-dependent one, we resolve our delta function as a Fourier integral, writing 2 pi times the delta function energy is minus infinity to plus infinity, e to the I et over h bar times dt. Yeah? Now, if we insert that here and write that in length, what we get is sigma from omega 2p alpha f h bar over omega. Still get the sum. And now we get the integral. Okay, I write it here because I always forget dt in the end. You don't mind. E to the I omega t, e to the minus ef t, e to the plus e I t. So that's essentially from here. And now we write our matrix elements I, p times d, and this is adjunct f, f, p times d. Forget the v, but okay. Initial, and I think that's more or less it. Yeah. And now you see, we would like, of course, to apply the closure relation, right, to get to the lower formula. But this is not possible because here we still have another dependence on the final energy, on the final energy states, because the energy EF stands here. So it's not only just the sum over the states, which gives unity, but here it's a phase. So we have to get rid of the phase. So how we do that? We do that by realizing that essentially this e to the I ft is nothing else but applying the full Hamiltonian e to the I ht onto the final state. Yeah? This is energy F times T times F, because that's of course an eigenstate of the Hamiltonian. And therefore, we can simply include these states by putting basically these phases. I mean, this is just a complex number, so we can put them anywhere inside and put them at the right position. That means we leave all that up to here, and from here we say it's now all the same. We get initial p times d velocity, and now here we put our e to the minus EIHT, yeah, on f, and the other one we take all the way to the end. And put it here, e to the plus I EHT on E. Yeah? So this gives plus the I energy E initial here, and this one gives minus the I energy final from here. Yeah? And now you see this is already the formula I've got up here in the first line, from where it's of course trivial to apply the closure and to get to this nice result and the formulation of photo absorption in terms of the dipole correlation function. But this is of course not the reason why I told you that. The reason is now on the next slide, because now only the approximation starts, and this has now to do really with the Born-Oppenheimer approximation. So far this was completely general for any kind of system. Yeah? We have not specified it to molecules or whatever, it's just single photon absorption. Now we realize for a molecule, of course, we have in the Born-Oppenheimer approximation our initial and final potential surfaces shown here. Let's say this is a binding one initially where our molecule sits, and the final one, let's take it repulsive. And then we have this photo absorption which takes us from here up there. And now this is another approximation which is very good, of course. It's called the conical approximation, the vertical transition, because the photo absorption is electronic, it's so fast that the nuclear configuration does not change. So we don't go from here to there to another distance of your molecule, you just go straight up. I should say this R and B is just a diatomic molecule. So you think of it something like that, 2 atoms, this is mass A, mass B, and this is our coordinate, oops, what was that? Our coordinate R, A. Okay, so now we know we have 2 potential surfaces. And the next thing we realize, which is now very nice, of course, that the dipole moment is basically constant due to this vertical transition in the nuclear coordinate. So essentially, this integral here over the initial state is vibrational for the capital R coordinate, vibrational wave functions, atomic motion, and the dipole addresses the electronic. So that's an expectation value over the electronic coordinates. This is where the photon gets absorbed, and it does not depend on the nuclear coordinates in lowest order approximation, so we simply can take this dipole as being constant out of this integral. Yeah? So we take the 2 dipole operators out, and that leaves us here with this formula, and this is now very important because this has now the structure I mentioned in the beginning. Essentially you have a propagation backwards with one Hamiltonian, H initial, that's this potential curve. And then you have a propagation forward for the same time with another Hamiltonian, this excited state Hamiltonian. And this is this typical form of the quantum fidelity Hamiltonian, where they have the difference of 2 Hamiltonians in the exponent. But of course, you know, we cannot just take simply this together in the exponent. This is another approximation, which is of course justified here because it's a short time approximation given by the Baker-Hausdorff formula. So the 0th order term allows you to write this basically as the difference then of the Hamiltonians in the exponent. Of course, there are other terms with commutators and so on, yeah? But the 0th order term is this one. And this is now very nice. Why? Because, I mean, so far these have been operators, yeah? Kinetic energy and potentials. But since we are in the Born-Oppenheimer approximation for molecules, the kinetic energy is the same in both initial and final Hamiltonians. So if we subtract them, this drops out, and we are only left with a C number, the difference of the potential. So that's just a phase. And that gets rid, of course, of all the complications of quantum mechanics, if you wish, because now we can evaluate essentially our time integral. I mean, oops, it's shown down here again. So this is now just the C number, delta V, difference of the potential, times time. And here's another phase, e omega t. This together gives this delta function here, delta of delta V minus omega, and this we only have now to average over our initial vibrational wave function. And this can be done basically analytically. We take out the delta function, 1 over the derivative, like always, find the right root, r equals r omega, where omega is given by basically making the delta function 0. And what this amounts to in the end, and this is why it's called reflection principle, is really that what you observe as a photoelectron spectrum, absorption spectrum here, this is the energy axis, is kind of a reflection of your molecular vibrational wave function in the initial state. Because that's essentially reflected at this upper surface, and it can even take that further by basically expanding your wave function here, or your potential about the minimum, the main point, where your quantum transition takes place in second order. And here you make a linear approximation about this point where you go up mainly. And if you plug that in, you can get even the relation between the width here of your potential or your wave function and the width of your photoelectron spectrum. And this is shown here. Okay, now comes the last point to that one. So this I think Thomas will use. But the question is, can you take the reflection principle even so far that it applies for atoms? Just for atoms. And this, of course, is a bit crazy because, first of all, where are adiabatic surfaces for atoms? I mean, you only have electronic degree of freedom, what should be slow. And we also will encounter a second difficulty, but we will overcome both of them. So you can construct very easily an adiabatic surface if you wish, if you just take the radial dependence of your energy. Because you know that photoabsorption always changes the angular momentum. So certainly these two Hamiltonians from the initial state where you come to the final state will differ by a centrifugal barrier. This is always the case. Yeah? And this is sketched here schematically. Let's say you come from an S state, L equals 0, that's just your Coulomb potential. Yeah? For one electron, you can take hydrogen or any Z, hydrogen-like atom. And this is, let's say, your final state. You go to L equals 1. Here you add the centrifugal barrier and you get a very different quote-unquote potential curve. So fine, we have two Hamiltonians, as before, H0 and H1, L equals 0, L equals 1. That's the same general expression of the dipole correlation function. But now, of course, we cannot take out the dipole operators. The dipole operators act on the same Hilbert space, just the electronic coordinate, where the integration is over. That's just the electronic wave function. We don't have anything else. So what to do? Now comes the nice trick, and that has to do with the observation that essentially the dipole operator has the same radial dependence as the centrifugal barrier in a certain gauge representation. So we end up really with this formula for the electronic photoabsorption just in an atom, which has again the structure of this fidelity Hamiltonian, and then we can apply the Becker-Hausdorff form again. But of course the question is, how do we get rid of the dipole operators? And this is shown here. You see that in detail. So the difference of our final and initial state Hamiltonian is proportional, or is directly 1 over r squared if we go from L equals 0 to L equals 1. That's very easy to see. Yeah? 2 over 2r squared is 1 over r squared minus nothing, because L equals 0 is nothing. And now, and here comes the observation, the dipole operator in velocity gauge is just the gradient of the potential, and this is also proportional to 1 over r squared. And if you take the exact form, here now for linear polarization between Lm state, 1, 0, and the ground state, Lm equals 0, 0, then the dipole operator has this form, 0 squared root 3, 1 over r squared. So exactly the same dependence is here, which suggests, of course, we can express the dipole operator as the difference of these two artificial potential surfaces. And that means we can write our absorption cross-section right away in this form. Instead of the dipole operator, we have the difference of potential surfaces here and here. Yeah, and this one can show is really equal to this fidelity-like Hamiltonian, also seen in the molecular version, where it's very easy to take out the dipole operators. And why is that? This is because you can differentiate this expression with respect to time. Of course, the whole expression is not dependent on time, so it gives 0, and gives the first term where only this phase comes out, and the second term brings you down basically h1 and h0 differences of it. And that gives you then exactly the expression you need. I'm wondering if I should do that and we stop that and do the time tomorrow. Let's see what we have that. Yeah. So we have sigma of omega is now this prefactor c times the integral e to the I omega t. Initial state expectation value of this fidelity Hamiltonian, E final or E1, e to the plus EH0 of t. And yeah, dt I have already. Now we take basically d sigma by dt. This is of course 0, it does not depend on time. And if we take that inside here, then we get first of all, we get e to the I omega outside here, but the rest of the expression is the same, so that means we get e omega times sigma of omega. That's clear, right? And then we have to take this one, and here we can write this is minus c integral dt to the I omega t I, and now we write e to the I h1t h1 minus h0. You can think about that this is correct. While we discuss it in a second. Of course, one has to be careful with the sequence. You cannot take h0 by h1, yeah? But I can take h1 by h1, so I can interchange the sequence of the exponential and that one. So this is okay, because this is always next to its exponential. And this tells you, first of all, that we can express, if we want, our photoabsorption cross-section also in this way, by essentially dividing it by omega, and I forgot one e here, because here it comes an e down. So now we have to do that another time, but this is not so easy. Now we have a problem with the sequence of the Hamiltonians, because if you differentiate again, you do not get this difference here at this position, right? So what to do? Oh, you have to burn the lunch. Okay, it's a bit mean. Think about what I did going from the golden rule in the energy domain to this time-dependent expression. I changed my e to the I energy times time, so just a complex number to the operator. Yeah? Because it's always eigenfunctions of this operator. So what I do is essentially here, now I replace that again with the full Hamiltonian up here. So what I can write instead of this one, I can write I e to the I h0 t. So that's the same, yeah? Because I can take that out, that's just a number, put it on this side and take it in again and replace it with h0. So I take this out as to the I h initial, or e initial, sorry. E initial or E0t, yeah? And I put it inside here again, and then replace it again with the Hamiltonian. Now if I have that, I can differentiate that again. So I write sigma of omega equals, just from that one here, e over omega, the I h omega t, and the minus e h 1t. h1 minus h0 times initial. And now, again, d sigma by dt equals 0. No, I'm getting lazy, sorry. I omega t dt. I again get the phase out. So this gives me I omega sigma again, because I just get the identity expression as before, and then minus c over omega squared. That's an I think. And now comes basically on the left hand side this difference. Now h1 minus h0 e to the let's see. That's important. Sorry, it's it to the left. e to the I h0t, h1 minus h0 e to the minus h1t. This is okay because h1 is still directly here with h1, yeah, and h0 directly here with h0. And of course, from before we have here h1 minus h0. And now I can play the same trick, put it again on the other side, and then I can get basically the exact expression. I think I missed 1 omega here. Then in the end, sigma 1 omega equals, this is, yeah, I didn't get a new omega here because I differentiated h1 and h0. So if I put that on the other side, divide by omega, I get c over omega squared, and then get this integral dt e to the I omega t, and that's really the expression we had. I h1 minus h0 e to the minus h1t, h1 minus h0 e to the I h0t. Yeah? So that's really the expression we wanted. I can show that again. Where was it? Oh, it's there, right? Here's this expression. It's exactly now here derived from this one. Now comes the final basic trick we already know. We basically put with the Becker-Hausdorff formula this difference in the exponent, h1 minus h0. Yeah, and this is now very simple in general, because the difference is just the centrifugal potential, 1 over r squared minus omega, gives you the delta function. And this has now a very nice interpretation. Maybe my colleagues will jump on me if I say that. Because it tells you where, I say where in the atom the photon is absorbed, radially. Yeah, mainly at least. It tells you that the distance where the photon absorbed is given by 1 over the third of the photon frequency. Now, does this make sense? Now you have to think what you have to fulfill if you absorb a photon. You start out with an electron which is bound. It has on average 0 momentum. Yeah? You photoionize, your electron goes out, and all of a sudden has a finite momentum. So in order to fulfill the momentum conservation, your nucleus has to supply or take a recoil. It recoils and also gets a momentum in the different direction, though the sum is in the end still 0. Of course, you see only your electron coming out. The nucleus is so heavy that you don't realize that. And this relation tells you exactly what amount of recoil you have to get by your nucleus to compensate the photon electron momentum. And that means higher photon frequency leads to larger electron momentum. Of course, your electron goes out faster. And that means you have to absorb more closely to the nucleus to get a larger recoil. And that's exactly what this formula means. And here, finally, for you is a quantitative comparison. So this is for hydrogen here. That's the analytic formula you get out. Of course, you can insert hydrogenic wave function and just get this photo absorption cross-section. The energy variable is, of course, here scaled with the binding energy for the frequency omega. And this is a comparison to the exact result over many decades here of photon frequency in orders of the cross-section. Exact is hardly visible, but it's a dotted black line. Reflection principle is red. And what people mainly do for high energies, of course, insert a plane wave. Yeah? And then you see at high energies that's okay, but also this one does not do any worse. But at lower energies, this approximation is much, much better. I mean, this is 10 to the minus 2 in the scaled units. It's very close to threshold, and you still are okay with this approximation. And now comes the funny part. It gets better if you take more electrons. So for 1 electron, it's the worst. If you take more electrons, mean field approximation, of course, in helium, this is the result. And this is very, very close to the exact one, or the experiment in that case. Of course, this is a doubly excited state. You don't get that. I mean, it's a short-time approximation. You cannot represent resonance. This is just a mean approximation. But this is very close. Now you can think about it, why this is better for more electrons. I won't tell you that. You can discuss that later. You can tell me what you think. But what you also see here, I think hooks very nicely, is that you see this 1 over omega to the 7/2 dependence. We all know that for large photo frequency, the photoelectron cross-section goes down with the 7.5 power of the photo frequency. This comes out here as well. Yeah, and I think with that I should close, it's already late, and leave the time from space tomorrow as a starter. You will get upset about it, I hope so. But anyways, thanks for your attention.